Okay, so now what we're going to do is we're going to now work on the quotient rule and come up with a derivative shortcut rule for quotients. Now, just like the product rule, we are not going to be able to distribute the derivative over a quotient. We could do it on a limit as long as the limits existed, but we are not going to be able to do that on the quotients when we're doing the derivative. So we're going to take our two functions, f of x divided by g of x. So I want to take the derivative of this quotient with respect to x. I'm going to use the limit definition to develop the shortcut rule. So the limit as h goes to 0, plug in x plus h into your function, subtract your function, and that's all over h. And now, of course, one technique, remember that when we have complex fractions, you are going to multiply by your LCM, or your common denominator, basically. Right? So our common denominator, they really don't have anything in common, so I'm just going to multiply, and remember, by a form of 1. You're only allowed to multiply by forms of 1, or you're only allowed to add 0. So I'm going to start by multiplying by this nice form of 1, because I do not want to have my complex fractions in there. And I'm going to run the numerator times the numerator, and I'm going to remember to distribute when I distribute both of those through. And then the bottom, remember, we're going to leave in its factored form since it's already nice and factored. So we end up with, in the top, and the whole point of multiplying by this LCM when I distribute this through is this LCM times the first fraction, the g of x plus h will cancel. So we would be left with f of x plus h times g of x minus, and then when I multiply this times the second fraction, the g of x cancels. So I would have f of x times g of x plus h. And then down here in the bottom, I have h times g of x times my g of x plus h. Right? And again, now, this is very similar to the proof that we just did for the product rule. Remember, you are only allowed to multiply by a form of 1 or add a form of 0. So we're going to do very similar to what we did in the product rule. Some really smart person came up with a nice form of 0 to multiply by, or to add. I'm going to split this again, kind of similar to what we did. I'm going to do f of x plus h times g of x. I'm going to subtract f of x, g of x, and then I'm going to add f of x, g of x. And I probably should have put that in a different color for you. I don't think I can go back and do that if I ungroup. Let's see. Maybe if because I have that in there, it's not going to let me pick it. I'll just write over it then, because I want that to be in red. Minus f of x, g of x, plus f of x, g of x. And again, the only reason we're allowed to do this because my net gain here is I'm basically adding 0. Right? Let me just continue with the rest of this. So I have minus f of x, g of x plus h. And that's all over those 3 factors in the denominator. So h, g of x, and g of x plus h. Right? Now what I'm going to do is I'm going to conveniently kind of regroup here. Kind of do the same thing that we did before. I'm actually going to go ahead and the limit of a product is the product of the limits. Well, actually, let's go ahead and kind of rearrange these into a nicer form. So I'm actually going to put these two together, just like we did before. So we're going to do the limit as h goes to 0. And we have the f of x plus h, the g of x, minus f of x, g of x. And I'm going to put that over the denominator, h, g of x, g of x plus h. Good thing we don't have to do this every single time because it's a lot of writing. I'm going to distribute the limit over this sum right here. So I'm going to do the limit as h goes to 0. And then I'm going to group these two together. F of x, g of x, minus f of x, g of x plus h, all over all that denominator. Bring it along. Don't get lazy and not write it. All right, and once I get to here, I'm going to do the same factoring that we did before. This one has a common term of g of x. And the nice thing about this is notice that when I factor it out, it actually is going to cancel with something that's in the bottom. I'm not going to. I'm going to kind of show you there's a reason for that. I'm going to pull this out here. Over here, I'm going to pull out, they have an f of x in common, but kind of looking ahead when I'm doing my derivative, I really want the g of x plus h to be positive, so I'm actually going to pull the negative out as well, because that will help me get it kind of set up in a good form. All right, so we're going to come down here and limit as h goes to 0, and I'm going to pull some of these out as well to kind of work with this. I'm going to have my g of x times, when I pull it out, f of x plus h minus f of x. I'm going to go ahead and put the h over here, and then over here I'm going to put the g of x plus h. Okay, just rearranging it in a nicer fashion. And I'm going to do the limit as h goes to 0, and we're going to pull the we're going to pull negative f of x out. Okay, and again, the reason why I want to pull the negative out is because when I do that, that's going to allow me to make this one positive, and I'm going to write it first, g of x plus h positive, and then this one will be subtracting g of x. I'm going to put the h with this one, and then do the same thing I did over there, put the g of x and the g of x plus h here. Okay, so it's really just fraction rules and just rearranging. Now what that allows me to do is the limit as h goes to 0 of this, okay, because I can distribute the limit through. The limit of a product is the product of the limits, so I'm okay with that, and h is going to 0. I'm not going to simplify just yet. You'll see why in a second. I'm just going to leave this as g of x squared on the bottom, because h went to 0. And then times this limit as h goes to 0 of this one. Hopefully you'll recognize, hey, that's nothing more than f prime of x plus, I'm going to do the same thing over here. You're going to end up with negative f of x on the top, because h going to 0 doesn't affect it. On the bottom, we're going to end up with g of x squared. And then the limit as h goes to 0 of this difference quotient, that's nothing more than g prime of x. And the reason why I didn't cancel when I was over here was because if you'll recognize, I really have a common denominator, and we prefer the quotient rule written as a fraction, as a quotient. So this is going to end up being g of x times f prime of x, this minus f of x, g prime of x, and since they're both over the same denominator, I can simply put it over g of x squared. So what we've shown, and this one's going to be one that you're really going to have to work on to memorize, that the derivative of f of x divided by g of x, when you have a quotient, you are not going to be able to distribute over the quotient. It is this very complicated formula where you take the bottom times the derivative of the top minus the top times the derivative of the bottom all over what was in the bottom squared. Now there are many mnemonics for memorizing this. When you're taking a look at it, a lot of times they call this the low and this the high. And so a lot of times you will see this rule written as low the high minus high the low, which basically means derivative of the low, over the low squared, kind of giving you a way to memorize it. There are all sorts of songs out there that you can basically Google some songs. There's one to Old MacDonald Had a Farm. There's all sorts of different mnemonics. It doesn't really matter how you memorize it, but you have to memorize it. This one is the harder of the two between product and quotient rule to memorize because of the subtraction. Subtraction is not commutative, and so you do have to always make sure that you always do the low as the first function times derivative of the top, and then minus the top times derivative of the bottom. It has to be in this order, or else you're going to mess up your derivative. So you want to be very careful about that one because it's not commutative. So again, just reminding you, the incorrect quotient rule would be to distribute over the quotient, and again, you get 0 credit for this on the AP and on my test. So if you ever see a quotient and you just distribute, this is going to give you 0 credit. You want to make sure that you have your quotient rule. Now, of course, all of this is provided that g of x doesn't equal 0, because that's going to give us a division by 0 problem. This is just reminding you that we are not commutative for subtraction, so order matters. And so you have to make sure that the terms of the numerator in your rule are in the correct order. Okay? This is recapping the high-low. Sometimes they change the low to ho because it rhymes with low, and so they can do things that have to do, if you've ever watched the Tim Allen show where he was the handyman or whatever, and his neighbor, where he used to go hoity high, neighbor and all that stuff. So that's one way to remember it. You can do the dwarfs, you can sing songs, Santa Claus in a hurry. It doesn't really matter, but you have to kind of get this rule down in some version. I don't care how. Here's a YouTube. I'm not going to watch it right now, but you're welcome to go click on this or type this in and watch. There's a little song that you can have. You can sing it to the tune of Old MacDonald. That's not my version. I just remember low-de high minus high-de low all over low squared. And I get that in, but you must memorize it. Okay? All right, so let's do a couple of examples here on how the quotient rule is going to work. So on this one, here's my high and here's my low. So I want to take the derivative using the quotient rule. So part A here. So we do, first let's label it. We always want to use good mathematical notation. So dy dx equals, I have a quotient, so I'm going to do low, x squared minus 1, d high, 4, minus high, 4x minus 2, d low, 2x, all over low squared, x squared minus 1 squared. Now, just as a comment about simplifying, you are pretty much never going to multiply this out. Factored is always best, and so what's in the denominator squared, we always leave it. The top, however, is not factored, so if I did need to simplify this, I would look for a common factor. This has a 4, and if you think about it, this is a 2, and this is really technically 2 times 2x minus 1. So I really do have a 4 in both of these. So I could pull out the 4, but that's a constant that's not really going to help me any. So I am going to go ahead and take this one and multiply it out. So distribute, and I'm going to collect like terms. I would like you to be careful if you are simplifying that this negative will distribute. And so you want to make sure that you're very careful when you are simplifying these if you are going to distribute. All right, so we would end up here with 4x squared minus 4. And then we would have 8x squared, but I'm subtracting. And then we'd have minus 4x, but I'm subtracting. Do not multiply out the bottom. Again, factored is better, and it is factored in the bottom. And then we collect like terms, so we have minus 4x squared, and then we have our plus 4x and our minus 4. And then if we can, if this does factor, that would be great. Let's pull the negative 4 out, see what we end up with. X squared minus x plus 1 all over x squared minus 1 squared. And if we take a look at this, I do not believe that there's any way for this to factor because it would have to be x minus 1 squared, which does not give me the correct middle term. You could check your discriminant, but that doesn't factor any farther. So that's the idea. If you aren't going to use it and you don't have to simplify, you would stop here. And there would be a lot of cases where we're going to do a problem where in part A, in the free response, they're going to ask you to find the derivative. You should stop right here in part A. If you need to use the derivative in part B, then simplify it in part B, because you don't want to lose credit for algebra mistakes you've made in this process. You want to get credit for having the correct derivative here. Okay? And I'm going to leave you to show graphically the B. So I'm going to leave you to do the calculator and part B on your own, and because that's going to be fairly straightforward. All right, so example 4. Let's take a look at that one. Sometimes we still have to rewrite, even though, we have this. This is really a complex fraction. So the idea is we're not going to really like that in this form. And so when we rewrite it, what I'm going to do is go ahead and rewrite this and get rid of the complex fraction, because you really don't want to do a quotient rule within a quotient rule. What I'm going to do is I'm going to utilize the technique of using the LCM. So I'm going to multiply by a form of 1. I'm going to multiply by x over x, simply to get rid of the fraction that I have in the numerator. That's going to give me 3x minus 1 over x squared plus 5x, and that's a pretty good form for you to take your derivative. You're going to have your high is going to be the 3x minus 1. Your low is going to be the x squared plus 5x. So now I'm ready to take the derivative, dy dx. Oh, and how did I know I needed the derivative? Because I'm looking for the equation of the tangent line, which means I need the slope, which is going to be f prime of negative 1. If you want to call this f of x, or we could label it as, if we didn't want to come in and label it, because you can't really use f unless you label it, we could call this y prime of negative 1. Okay, so I need the slope, and then I'm going to need to find the point, which is going to be negative 1, and then y of negative 1, use the function to plug that in. We'll come back and do that in a second. So let's find our derivative, since we know we're going to need it. Find it, and then we'll plug in our value. So we're going to do our low d high minus your high d low all over low squared. So x squared plus 5x squared. Now, if we want to, we could simplify this, but really in this problem, since I'm really just looking for a slope and I'm not doing anything else, I'm going to go ahead and at this point go dy dx evaluated at x equal to negative 1 equals. Do not say this equals and put another equals and start plugging in. You got to label what you're doing. I'm plugging in negative 1. If you wanted to, instead of using this notation, you could have done y prime and then called this y prime of negative 1. Either way, but you have to label that you're doing the derivative at negative 1. And then we just simply do some arithmetic. Negative 1 squared is 1 minus 5, negative 4 times 3 minus negative 3 minus 1 is negative 4. Negative 1, negative 2 plus 5 is 3. All over we already figured out that this is negative 4, but I'm squaring it, so I get 16. We combine these together, negative 12 plus 12, and we get basically 0. Okay? So what does that tell me is happening for the tangent line at x equal to negative 1? We know that the tangent line is horizontal, which means that coming up with the equation, what I basically need to do is to know this y value. So I come back in, I'm going to calculate y of negative 1. Here's my y, or you could use this version here. Let's go with the original in case you made a mistake. 3 minus 1 over negative 1 is basically 3 plus 1 is going to give me 4 over negative 1 plus 5, 4, which is 1. So y equal to 1 is the equation of the tangent line. So we're basically still doing the same problem that we were doing before, except now what we're doing is you just basically have to use a more difficult rule to find the derivative before you can find the slope at a certain point.